the presentation fills out my screen?
Sure, however you would like to do it.
All right, very good. Well, welcome everybody. As Lucas said, my name is Enrico. I do work for Composite Technical Services, even though we do differentiate the cylinder business through another company which we call SETMA Technologies. It's primarily the company that deals with composite cylinder technology. So I'm going to start introducing a little bit the market trends for the use of CNG composite cylinders, and then delve deeper into what we know as a Type 4 technology, which is a whole composite solution and the lightest weight solution currently available in the market. So if we look at current market trends, you'll see that the use of CNG vehicles is still very low, and lately, primarily in the last 6 years, we've seen a new demand for this type of vehicles because of the low cost of the fuel. What we're seeing is there's currently about 2.5 million pressure vessels in the market, ranging from Type 2 to Type 3 to Type 4. I'll go through what those mean in terms of technology in a little while. We're seeing primarily European manufacturers like Fiat, Mercedes, or Citroën creating dedicated lines for CNG powered vehicles, even with a dual fuel system. And also buses are particularly, we're seeing a lot of new bus technology being pushed into the market, primarily because of the low emissions of pollutants like NOx's and other sulfides. Ironically, the leading countries currently that we're seeing using primarily CNG are in the Middle East, Iran, Pakistan, and in South America with Argentina and Brazil. And we're also seeing India right now starting to push a lot of this alternative fuel technology into the market, as well as Italy and the rest of the European countries. These are represents some of the market trends that are expected with fairly aggressive growth of about 18% per year. This was done by the International Association of Natural Gas Vehicles, which is predicting that there will be about 65 million vehicles worldwide by the end of 2020. So current data for the U.S. market are not readily available, but with the discovery of cheap gas, especially here in the northeast region, that there's an expected likely growth of for NGV vehicles. We'll skip this. Let's delve into the technology. So what do we mean by Type 1, Type 3, and Type 4? So you see what we typically refer to as Type 1 or CNG1 are traditional technologies for pressure vessels made entirely of metal. And that could be either steel or aluminum, depending on the type of pressure that it has to maintain. Then a new technology, relatively new technology, made use of a hybrid structure where you're still using a metal as your main vessel, but you're going to also use plastic reinforcement fibers, primarily glass in this case, to strengthen the cylindrical section. So you see the fibers are only applied to the cylindrical section and not the domes. So this is perhaps the most popular hybrid technology out there, and there is a good net saving in weight, and prices can be maintained almost the same as a whole metal technology. And this is becoming very popular because it's a good compromise between weight saving and and cost. Then we pass on to the Type 3 and Type 4 solutions. This is an example of a Type 3 here. The difference between the Type 3 and the Type 4 is in the type of liner used to in the technology. So, for instance, in the Type 3, we'll see the use of a metal liner, typically aluminum. It will be a unibody solution where the aluminum will be typically about 4 millimeter thick. So it's not going to be very thick at all, and it's not going to be a load-bearing structure, but it's simply used as something to wrap your fiber onto, and also be inert with the gas that it carries. Likewise, in the Type 4 technology, now we're using a thermoplastic liner, typically polyethylene, high-density polyethylene or a nylon, and equally fully wrapped with FRP. So to summarize, if we take a 50-liter tank, which is about 15 gallons, and we compare the weight based on the several technologies, you can see that we go from 40 kilograms, or about 88 pounds, for a Type 1 system, and you can see the savings on this column here on the right as you go through the various technologies, all the way down to a Type 4 system, which gives you the highest possible saving with a 65% reduction in weight. Now that's actually meant, there's not a column here that shows the cost comparison, but the cost is probably proportional to that weight saving, meaning that there's not an actual improvement in the cost to weight structure. So the part of it, and I'll show you to the very end of the presentation, has to do with the cost of carbon fiber, which is predominantly still used in the aerospace industry and therefore not benefiting from a good economy of scale yet. So let's look a little bit more at the Type 4 cylinders. Like I said, Type 4s is the plastic liner with typically a carbon fiber resonance wrap on top, as is showed in the left-hand side picture. The advantages are the lightweight, is we'll say the low prices to the volume ratio, basically the ability to carry so much more weight compared to its volume, compared to the steel. The seamless liner, which is required by the NGV2 DOT regulations, enables the good long-term pressure tightness, meaning that there's no leakage of the gas during service. And obviously the use of composites, it's really beneficial to the corrosion resistance. This is a schematic that pretty much illustrates what I was just saying. You have an inner plastic liner, which is the inner ring shown here. You typically then have a carbon fiber layer, which represents your structural components. And typically, we will finish it off with a glass fiber layer, primarily for impact resistance. Carbon can be quite fragile and not very good under impact conditions. And obviously, these products have to survive. Obviously just as transportation, but certainly also during service, it's not unusual to knock them or somehow dent them, and that's what the glass fiber primarily does in this case. Let's start see how we can manufacture the plastic liners. So plastic liner production is typically done with a technique known as rotor molding. Rotor molding is a very common technique known in the plastic industry, thermoplastic industry. You can see you start off from a powder, which is then placed in a mold, the molding is then closed, and then we go to the right-hand side where you start applying heat and rotation. That guarantees that the powder is basically projected towards the side of the walls of the mold, and the heat guarantees that you have the plastic starts melting. Then, while spinning, you start cooling it down, and at the end of the process, the bottom right, you have your part. This is a very common technique and the one primarily used by most producers out there. This shows you a schematic on the shape of the mold that we typically use and of a typical vessel, and it shows you several types of design for the metal boss, which is perhaps one of the most important aspects of the technology. Basically, one must ensure a very good fit between the metal boss, which is necessary for the coupling between the vessel and the rest of the equipment used to basically hook up to it, which obviously has to be under high pressure. Probably failed to mention, but these products function at about 3,600 psi during service, and they're designed to sustain up to 8,000 as a catastrophic thing. So the secret really is the ability to embed the metal boss into the plastic and do it without leaving any sort of interface where the gas could escape and leak. And this is an example, a real life example of technology that we developed at SETMA. You can see on the left a rotor molding mold, and on the right what the final product looks like with the metal boss embedded into it there at the center of the dome. The next step typically is development of the code and the laminate buildup. Most of you may or may not know that the strength of the composite comes from the fiber they use. So that's why carbon fiber are so popular. They're very lightweight, but also many times stronger than steel. The caveat, though, is that the load is only carried along the direction of the fiber. So it is very important to build a laminate structure that embeds several angles of this fiber in order to maximize the load carrying capacity. So this is done by computer modeling primarily, where you need to carefully understand where the highest loads are and how to count because if you're not going to build up your laminate right, you may end up with a very high thickness shell, and in that case you're going to pay not just a weight premium but also a cost premium. And obviously with the carbon fiber selling at $14 a pound, you want to be as optimized as you possibly can. This is the next step in the production. This is where the fun is. You start winding your product, at least fun for me. It's typically done in machines like the one that you see up on your screen right now. It's a CNC controlled machine, and it comprises of the now rotor molded component, which acts as your mold, and you wrap your filament around it. In this case, we have two components that are being done at the same time. You can see as much as 3 typically in the business, and for smaller components even up to 6. But that all helps just maximize production and speed. So I have a small video to show you now. Hope you can all see it. But it shows how the machine works. You can see that there's a combination of angles going on here. This is the situation where we're adding angles that are very tight, and in this case we're adding a hoop angle. Both contribute greatly to the ability of the vessel to sustain its pressure during service. This is a first test at about 8,000 psi as described. And we do that typically using just water pressure in a concrete bunker just outside of the plant. So let me continue the presentation by going to what the testing showed you. That particular one was a catastrophic failure. Like I said, the product is usually designed to sustain up to 8,000 psi, which is about a factor of 2.5 over the normal working pressures. But the real trick when you design these products is to design them for not for catastrophic failure, but rather for a premature failure, if you will, through leak and not rupture. That minimizes the potential of turning the debris into projectiles if it was to explode. So this is a typical system, and this is done during cycling, back and forth, so increase the pressure, lower the pressure until we see failure. Similar test is called Bonfire. Again, the product is designed to vent before rupture, again to avoid any explosion or fireball or any sort. And there are certain requirements, of course, for it to survive. Penetration test is typically done with caliber 38 gun, a rifle, and again the product is designed not to rather obviously the bullet will pierce through the shell, but the cylinder is designed not to explode in those conditions. Another type of testing is known as drop test. As you can see, you can use a forklift and then drop it from several feet of height. These are done also at different angles. There has to be a certain resistance of the product to impact, and that is to simulate primarily accidents. Finally, another testing is typically environmental exposure, which includes acid attack, salt water attack, and whatever could potentially cause stress corrosion of the system. And this is how it will typically be tested. So starting again from testing one, this is what the product looks like under catastrophic failure. You can see that the amount of debris is not contained. The fibers don't really go anywhere, and also the liner inside is not badly mangled, but rather it's filled through a single line. Then this is another type of test where again you have to destroy the product, but after fatigue testing. So typically you go through 30,000 cycles, and then you will test it catastrophically. Again, the product has to survive at a certain pressure. This time it could be a lower pressure, but it has to be within 80% of the design burst pressure. So 80% of 8,000, which is about 6,500 psi. Similarly, for acid attack, again, it's a certain amount of hours with a pre-pressurized container, and again, catastrophic failure to test the resistance to acid attack. We currently have designed two types of CNG Type 4 cylinders, a 15-gallon for sedan application and a 50-gallon for bus and trucks. Our typical construction includes what I just showed you, but we also typically add a foam dome for protection of the dome parts. Not much more to talk about here. Let's see what else we got. So this is what a typical sedan will look like. You can see that what a 15-gallon or 50-liter system would be able to carry here. We've done a little bit of math, and that would mean gasoline equivalent, it would be 12.7 liters. I believe that the gasoline equivalent in gallons is about 4 in that case. So the range is still fairly limited as far as that is concerned. And on the flip side, on buses, we have a lot more space, so we can use larger size vessels. And in this case, you know, we designed a product that was 50 gallon. I believe that that's a 15 gallon of gasoline equivalent, and that pretty much matches what a regular sedan will probably be able to do. And typically in a truck or in a bus configuration, we will probably use like 4 or 5 of these, usually at the top or at the bottom of the chassis. This is one of my last slides. I have one more to show you some of the cost analysis, but this is kind of a snapshot of the amount of qualifications that are required to get DOT approval to sell these products. So you all should feel fairly safe. The way to read this chart is to show what would happen if you ever changed any of these parameters on the left. So for instance, if you ever decided to change the fiber manufacturer, then you would have to repeat all the tests that are marked with an X. Same for, obviously, changing the plastic liner or the fiber material requires you to pretty much start from scratch, as you can see. Changing the resonance material would only have you focus on probably about half of the testing required. And there is a bit of leeway for changing dimensions within 20% of the original dimension, where you would only have to do 2 tests, and et cetera, et cetera. What this means is, and identifies perhaps one of the barriers to entry into the market, where it is costly to do all this testing, and it is often more costly to change your design or provide even larger or smaller type of dimensions. Just to finish, I was going to show you what the production cost of one of these vessels could be, specifically for our 50-gallon tank, or as I told you, 14.3 gallons equivalent. We concentrate on this pie chart on the right that identifies the cost of each individual component, with the carbon fiber obviously being the biggest currently, at 63% for these larger vessels. We also have a cost for the liner of about 20%, and the remainder is resin, glass fiber, catalyst, and dome protection. But this gives you an idea, more or less, of what it would cost to make one of these things. Currently, I would say, if you had to give a round figure, it's about $2,000 in materials cost for this type of, and with some manufacturing on top, for this type of vessel. And therefore, there's still a fairly limited use because of this. If you were to compare this to steel, the easiest thing to do is to divide it by the volume, and standards would have it that you would use a metric system. So if you typically quote the cost of these products in dollars per liters, and this product will probably fall between a $9 and a $10 per liter, which is fairly low for the time being. But obviously, the market is pushing us to make it cheaper and cheaper. As a comparison, steels would have a cost of about $4 per liter, more or less. And I'm sure there's some Indian companies that will be able to do it even cheaper than that. But that's pretty much where the technology is right now. So a lot of it is hinging on optimization. Typically, use more glass than carbon, and only use the carbon when needed, and more importantly, also the weighting of a cheaper carbon fiber in the market. And that concludes my presentation for the day.
Excellent. Well, thank you very much, and thanks a lot, Enrico. We don't have any questions at the moment, but I will go ahead and pause and wait. So if anyone has any questions, please go ahead and type them in now. Hey, Enrico, I do apologize for using your Composite Technical Services email address. If you wanted to really quickly, you could edit your slide and share your the SEMPA email address, perhaps.
Oh, I see. Let me do that.
Great. We've got a quick question for you here, Enrico. This is from Mick Torek. He wants you to talk quickly about wire tough type cylinders, if you could.
I beg your pardon?
His question is, well, it's more of a statement. It just says, talk about wire tough type cylinders.
Wire tough
Yeah.
cylinder.
Hey, Mick, sure. Mick, could you please clarify? I've actually unmuted you, Mick, so if you have a way of talking, then you can go ahead and speak.
Yes, can you hear me there?
Sure can.
There's a supplier on the market. The brand name is WireTough. Supposedly I would gather, instead of the carbon fiber, they wrap the cylinder in a wire, is the way they describe it to me. Me being a novice and a user. The cylinder, one of the advantages is the sunlight doesn't doesn't deteriorate the fiber. They're on the market, and I'm leery of buying them. I'll be quiet and let you answer that, Enrico.
All right. I do know what you're talking about. I have come across a wire tough, I believe it's called. The gentlemen of Wire Tough, they are actually using a wire made of steel. So they elected to pretty much take the design that I described as a Type 2, which typically uses glass fiber. But as you suggested, a steel wrapped, a steel wire would not have the drawbacks perhaps as UV destabilization as resin. I should point, it's not the fiber that degrades, is the resin matrix that does not have or can not have good UV stabilization. There's a lot of advances in resin systems that have, in fact, good UV stable life. So much depends on cost analysis. I can't speak enough of whether the Wire Tough guys are good or not. I mean, I have heard of their technology. I think it's very interesting use. I do believe they claim that there is a weight saving compared to a Type 1 without necessarily increasing the cost. So I do know, however, that they do use resin to finish their product in order to protect their wires. So there's something to consider in that case. I'll be happy to answer you privately if you have more questions on it.
Excellent. Very good. Thanks, Enrico. I've got one more for you, and I'm not sure if you have this information readily available or not, but Mick was also wondering what the dimensions of the 50 gasoline gallon equivalent cylinders are in inches.
So that was a 15. I should clarify. No, 50.
Okay.
50 gallons is the volume of it. But what you need to consider when you do the math is that you are compressing gas at 3,600 psi. Then you take basically a cubic foot of gas compressed at that pressure, and you take the BTUs that would, and then you compare it to what a gallon what the BTUs in a gallon of gasoline. That's how you come up with a gallon of gas equivalent. So a 50-gallon tank can only pretty much carry about 15 GGEs, or gallon of gas equivalent. And the dimensions that are shown here for that particular case, 455 will be, bear with me, for inches. So you're talking about a diameter of about 18 inches and a length of about 700 inches. And you know, the length and the diameter can vary while maintaining the same volume. So you could have, this is a fairly skinny cylinder, if you will. When you look at the aspect ratio, you could have a fatter cylinder, so something that is shorter and stubbier that carries pretty much the same amount of volume. Obviously, a change in diameter has a larger effect than a change in length as far as volume is concerned. Does that answer the question?
I believe so, Enrico. I think you've got it. So I don't see any more questions. I guess I encourage all of you to reach out to Enrico privately if you'd like. Yes, Mick said that did answer the question, so thank you. All right. Well, great. Thanks a lot, everyone, for joining us. I, or Tyler Palmer, or Matt Stevens-Rich here at Clean Fuels Ohio will be in touch with more registration info for our August webinar. Our August webinar will be working with the LDCs. So make sure to tune into that. Let's see here. I will also be sending out a recorded version of this webinar for future viewing for you all. And that's all I have. So thank you very much for participating, and thank you very much for your time, Enrico.
You're welcome, Lucas. Thank you very much. Bye-bye.
All right. Take care, everyone.